In July 2024, a structural reliability failure neutralized 8.5 million enterprise machines. A routine software update triggered the global collapse, exposing the fragility of the modern digital infrastructure that enterprise organizations rely on daily. This diagram illustrates how modern processors separate system resources into concentric privilege levels. Out here in Ring 3, or user mode, you find standard software like your web browser or a word processor. Ring 3 provides an inherent safety buffer. If an application encounters a critical error, the operating system simply terminates the isolated process. The app crashes, but the rest of the system remains stable. At the absolute center is Ring 0, also known as kernel mode. Code executing in this layer has unrestricted access to physical memory, the CPU instruction sets, and the underlying hardware. Endpoint detection and response platforms, like CrowdStrike Falcon, operate deep within this inner circle. Running a driver like csagent.sys in the kernel provides early boot visibility to intercept malware before user space services even load. This level of access also makes the security agent highly resistant to tampering. This high-privilege access requires a severe architectural trade-off. Unlike the isolation of Ring 3, any unhandled exception in Ring 0 compromises the entire CPU state. By placing security infrastructure in Ring 0, organizations accept a specific risk. A localized software bug in a vendor's update has the authority to trigger a system-wide kernel panic. On July 19th, CrowdStrike pushed a routine threat definition update to the Falcon sensor, known as Channel File 291. This update delivered a new inter-process communication template, built to evaluate named pipe execution and block command and control frameworks used by cybercriminals. This diagram shows the logic flaw at the heart of the crash. The new IPC template was programmed to define exactly 21 distinct input parameter fields. However, an integration failure meant the code invoking the interpreter only supplied 20 input values. When the system attempted to access that 21st value, it produced an out-of-bounds memory read beyond the end of the input data array. This parameter mismatch evaded multiple layers of CrowdStrike's internal build validation and stress testing before it was deployed. Because this out-of-bounds read occurred within the privileged csagent.sys driver, the Windows operating system could not gracefully handle the exception. The kernel immediately initiated a panic sequence to protect the system, manifesting as a blue screen of death. A rudimentary C++ parameter count mismatch neutralized 8.5 million machines. Because this error executed with ultimate system privileges, it disabled more computers than the most devastating malicious attacks in history. In the standard Windows boot sequence, the operating system initializes hardware and kernel drivers before the network stack or remote management services ever come online. This timeline shows the dead agent race condition. The CrowdStrike driver initializes almost immediately upon power-up. The corrupted driver crashed the kernel before the machine could establish a network connection. This trapped systems in an infinite boot loop, unable to receive a fix. CrowdStrike rolled back the corrupted file in the cloud within 78 minutes, but because the affected machines were trapped offline, they could not download the reversion. Recovering these endpoints required physical intervention. Administrators had to manually boot each machine into a recovery environment to delete the driver file by hand. This manual process hit a massive logistical hurdle: Microsoft BitLocker full disk encryption. To access the hard drive and delete the file, administrators had to locate and manually type in a unique 48-digit numeric BitLocker recovery key for every single affected device. In many cases, the internal servers used to manage those recovery keys were Windows machines that had also crashed, creating a complete circular dependency. This microscopic logic error cascaded into a physical bottleneck, converting millions of encrypted enterprise endpoints into impenetrable bricks that required individual manual salvation. The technical failure soon translated into a macroeconomic crisis, most severely for Delta Airlines. While other major U.S. carriers resumed normal operations within 72 hours, Delta's disruption continued for 5 full days. The disruption resulted in over 7,000 flight cancellations, stranding approximately 1.3 million passengers. This prolonged meltdown was caused by Delta's heavy reliance on Windows-based servers to run its critical crew scheduling and tracking systems. When the tracking servers finally came back online, the scheduling software was overwhelmed by a massive backlog of updates and reassignments. Flight crews were left waiting for the unresponsive system to process their assignments until they hit their legal flight time limits. This left functional aircraft without staff, placing crews in planes in the wrong locations for subsequent flights, and creating a state of systemic gridlock. Delta reported a total financial impact of roughly $500 million due to lost revenue and increased operational expenses. The airline eventually sued CrowdStrike in Georgia, alleging gross negligence and computer trespass. CrowdStrike responded with a countersuit, seeking to limit their legal liability to the fees paid under their existing software services agreement. CrowdStrike's defense focuses on Delta's own IT infrastructure and their decision to decline technical assistance during the recovery effort. The Delta crisis demonstrates how complex logistics are now tethered to the stability of third-party kernel drivers, allowing a vendor glitch to escalate into a $500 million disaster. This outage has changed how the industry views kernel-level endpoint protection. The existing model, which grants third-party security software unrestricted access to the operating system's core, is now being replaced by a more isolated architectural model. Microsoft's response to this vulnerability is the Windows Resiliency Initiative. The primary goal of this initiative is decoupling third-party security agents from the operating system kernel. This technical matrix compares the traditional driver model with the new Windows Endpoint Security Platform, or WESP. WESP shifts the execution ring for security tools. Instead of running in the kernel, these agents will now operate in user mode, or Ring 3. Security vendors have long resisted leaving Ring 0, arguing that user mode execution makes them vulnerable to tampering and limits their ability to analyze system calls. Microsoft designed WESP to address these concerns by providing secure APIs. These allow antivirus programs to analyze system events and maintain tamper protection. This provides a new crash protection guarantee. If a security agent encounters a logic error, it will be contained by standard process isolation. The agent will crash, but the operating system survives. Microsoft is also addressing the dead agent bottleneck that trapped so many IT administrators offline. They are developing a feature called Quick Machine Recovery, designed to execute targeted fixes on unbootable machines remotely. This eliminates the need for physical intervention, ensuring that a faulty driver can be rolled back over the air even if the operating system fails. The legacy of the July 2024 outage is a technical pivot towards system resilience. By building platforms that isolate security tools from the kernel, Microsoft is addressing the critical systemic vulnerability, where a single software defect can force a global system-wide collapse.